So today we're going to finish up our chapter about integrals, and I thought I would start out by looking at the very beginning of this course when we talked about functions and whether they had any value or not. Well, functions usually related to two variables. We had one dependent variable like, say, velocity, and one independent variable like time. And then there was usually some equation that related those. That was your function. V of t, say, is t squared. And then you would have some type of relationship. Now, the value of that, yes. You give it a time, you plug it into this function like time 3, and it gives you at 3 seconds that the velocity was 9 meters per second. So functions do have their value. The next thing we learned about was limits. Limits ended up not really having much value in real life as actually finding something out you were looking for. But one use we used for limits is we wanted to find the slope right here at some point t on this graph. And the only way we could find slope was to take another point a distance away, t plus h, and find the slope in between those 2 points, which was v of t plus h minus v of t all over h. But that was the slope of this line. To make it the slope what we were looking for, the instantaneous rate of change, we took the limit as h approaches 0. So we did use limits to actually find something of importance, and that we called the derivative, because we got a new function called v prime of t that found the slope of this line. Well, the question is, are slopes important? Well, if you look back to see what the slope is finding, it's finding a change in the dependent variable with respect to the change in the independent variable. So the units give things away whether they're of value or not. What you're going to get is meters per second per second. So what it's telling you is how fast that velocity is increasing or decreasing, depending on whether it's positive or negative, and how much that is. Now, it turns out that we didn't have to do the limit every time because we used this formula to come up with a shortcut, and we found out that v prime of t was 2t. So you could plug in 3 to that, and you would know at time 3 seconds that the velocity was increasing at 6 meters per second every second. And that, again, was value to us. Now, if you took another derivative, it becomes less value. Do you want to have meters per second per second per second? Maybe somebody could get some use out of that, but it becomes less meaningful. So we really want to know, yes, we can take derivatives, but what's the value of them? Anyway, we then did 2 chapters of derivatives. In the second chapter, we looked at all kinds of applications. So we found out many times derivatives really do have values. Well, we're focusing in this chapter not on derivatives, but on integrals. Well, limits came into effect again because we decided it might be a good idea if you had v of t and t to find the signed area between one time period and another time period. And the way we did that was to make these little rectangles. And we did it by picking a value in here called a time period called c sub k, and we multiplied it, the velocity at that time, the dependent variable, times the change in time, the change in the independent variable. And then we added them all up. And then, to make it perfectly accurate, we took the limit as n approaches infinity. So their limits again became valuable, even though we're not using them to find some specific answer. It allows us to find this infinite Riemann sum, which we called, in shortcut form, a definite integral. And we've now found a lot of uses of definite integrals in this chapter. Now, to find out if definite integrals have value, again, you can do it with the units. Just like up here, we took the units to be meters per second. Here, what do we have? Meters per second times seconds. To get the area in here, we're multiplying these units times these units. So what do we get when you go meters per second times seconds? You get meters. Well, is that something we want to find? And I think, yes. We discussed this yesterday. That's the change in position from time A to time B of something that's moving. We even gave it a name, the displacement. So anyway, integrals, definite integrals have a lot of value. We've seen a lot of applications. Derivatives have a lot of value. But still, we have to be careful to know in a given case whether it's even worth doing. So let's give an example. Say you had the number of bacteria, B, as a function of T, where T was in hours. And this is in the number of bacteria. And say you had some relationship that B of T was 10 bacteria plus 5 halves T squared. So first of all, does the function itself have any value? Well, sure it does, because you could plug in a time like at 4 hours from whatever time 0 happened to be, and you could see that B of 4 was 10 plus 40 or 50 bacteria. So you would know 4 hours into the experiment that there were 50 bacteria present. So that had some value, but that's the only value the function has. Well, then there's this derivative formula. Should we see whether the derivative has value? Well, using our shortcut method, we can find the derivative of this and get 5t. So if we plug in b prime of 4, we get 5 times 4, or 20. Well, 20 what? Since this is a derivative, we can look at the units and it's going to be what? Bacteria per hour. Is that something of value? Yes, it tells us that 4 hours into the experiment that the bacteria, the rate at which they're growing is 20 bacteria per hour. But back here, when we took the second derivative of the velocity, it didn't seem to have much value. How about this time? What if I take b double prime of t? Now I get 5. Now what are the units going to be now? Because b prime of t are in bacteria per hours, and t is still the independent variable. So you're going to get what? Bacteria per hour per hour. So that's telling you that not only are the number of bacteria increasing, but that rate is increasing. And you might really want to know that. You might even be more interested in that than to know how fast they're growing. If that rate is really growing, then you can see that those bacteria might really be multiplying. probably any more derivatives is not going to give you a lot of value. So you want to know when it's a value to take a derivative. Of course, we're focusing in this chapter on integrals. So would an integral be helpful here? Well, what would you get if you took the integral from 0 to 4 of b of t dt? Well, we could do it, but before I do it, before I take and put b of t here and take the antiderivative and plug in the numbers, what am I going to get? Well, the units are going to be bacteria hours, because you multiply units when you take derivatives. Do I really care about bacteria hours? There might be some little use in there, but I think very few people have a use for bacteria hours. So in this case, taking the definite integral really didn't give us a whole lot of value. And you really want to know before you do something whether it's going to be helpful or not. Now, if the original function had been this, b prime of t is 5t, if this had been b prime of t and this was in bacteria per hours, then would a definite integral be a good idea? Yes, because then what would you be doing? You'd be taking bacteria per hour and multiplying by hours, and you get the number of bacteria that had grown between time 0 and time 4. And that might be something you really want. So, we're going to shift over and look at a couple of examples that are completely different than we've done before, but see if we can get from units whether integrals or derivatives are going to be useful. So, I don't know if you've ever been there, but there's the C&C coffee shop. It stands for Caffeine and Calculus. Currently, at time 0, has 300 young men and 20 young ladies present. But because there were so many men per lady, over the next 40 minutes, men start leaving at the rate of 3 men per minute. But the ladies, looking in the window, see, maybe we should go in there. So they start entering at the rate of 20 over the square root of t plus 1 ladies per minute. And my question is, how many of each, how many men and how many ladies will be drinking lattes and doing integrals 40 minutes from now? So what is it we're trying to find in this problem? We're trying to find the number of men and the number of ladies. But we don't have a function that tells you the number of men and the number of ladies. We have rates. This is men per minute. So how do you get men from men per minute? You multiply by minutes. So we can take the number of men, 300, this is the number of men, and subtract from that 3 men per minute times 40 minutes. And what do we get? We get men. That's what we were looking for. So we have 300 minus 120, or we only have that many men available. 40 minutes from now. A lot of them left. Now how about the ladies? Again, we have a rate, ladies per minute. But this time it's not a constant rate. So maybe calculus can come into play here. So what do we have? We have 20 young ladies, but they're coming in at a rate of this many ladies per minute for a certain number of minutes. So what multiplies in calculus? Definite integrals do. So we want to take the integral of the rate times the time. And you want to do it over a period of, we're accumulating ladies over a 40-minute period. And we can tell this because the units. We've never done a problem like this before, but when you take ladies per minute and multiply by minutes, you get what we're looking for. Well, now we have to reach in and say, do I know how to take that definite integral? Well, one thing you could do is take the 20 out front, and you could call this 2t plus 1 to the negative 1/2. But still, it's not in the form of u to the negative 1/2 du, so we do a u substitution. We let u equals 2t plus 1, and du is equal to 2 dt. So we can rewrite this, and now we have the integral, and this becomes u to the negative 1/2. And what does dt become? 1/2 du from here. And 0 becomes 1, and 40 becomes 81. So you get 20 plus 10. And the antiderivative of u to the negative 1/2 is u to the positive 1/2 divided by 1/2, or times 2. So altogether we get 20 plus 20 times the square root of 81 minus the square root of 1. So 160 young ladies came in that 40 minutes, so now there's 180 young ladies. So looks like maybe there's a lot of good calculus and coffee drinking to go on for a while, because we have a nice even match now. Okay, so let's look at one more example. You have a partially full swimming pool containing 8,000 gallons of water. Just as you start adding water at a constant rate of 1,000 gallons per hour, a hole develops. And that hole gets bigger over time, causing water to leak out at this rate. So as t gets bigger, the rate at which it's leaking out is going to be bigger. What are we trying to find out? Gallons. What do we have? Well, we have gallons here, but we have gallons per hour here and here. So how do we get gallons from gallons per hour? We have to multiply by hours. And what in calculus multiplies? Integrals, definite integrals. So what I'm going to do to get the amount of water 4 hours after you begin, take the number of gallons at the beginning and then add the number of gallons per hour times the number of hours, which is 4. But then I have to subtract, and I'm going to do this multiplication with a definite integral from times 0 to time 4, the gallons per hour, 150 times the square root of t times the number of hours. So again, a problem that we've never seen before, but we can see exactly what we're trying to get is gallons. So altogether we have 12,000, but then we have to subtract that. So what's the antiderivative of t to the 1/2? It's t to the 3/2 divided by 3/2, or times 2/3. So you get 12,000 minus 100 times 8 minus 0. You lost 800 gallons, so all together you have 11,200 gallons. So, able to do that just using our idea of what a definite integral is. Now this part B says, in how many hours after you begin will the pool again have 8,000 gallons? So it started out at 8,000, it's gotten up to that high, will it ever go back? Well, as that hole gets bigger, maybe it'll go back to 8,000. So what can I say? I can let X represent the number of hours. So I can say 8,000 that you start with plus 1,000 gallons per hour times X hours. And then I have to subtract 150 times the square root of T gallons per hour times T hours, but we're going to go from where? From now to X hours. And what do we want that to equal? We want to equal back to 8,000 again. So we have to solve that equation for X. Well, if you just take the 8,000 out of either side, you can see it comes down to solving the number of gallons you add equaling the number of gallons that leak out in those X hours. So, this side is okay. This side we want to get to look more like a function of X. So we take the antiderivative again, which we know is going to be 100 t to the 3/2. So you get 100 t to the 3/2, and you're going from 0 to X. So I can shift over here. You have 1,000 X equals, now it's going to be 100 X to the 3/2. Now, X equals 0 would be an answer, because we know at times 0 there was 8,000. But as long as I keep that in mind, I can divide both sides by 100, and I can divide both sides by X. So 10 equals the square root of X, so X equals 100 hours. So 100 hours from the time you started filling the pool, it will again be back to 8,000 gallons, and then it'll continue to decrease. So these are just two more examples. What I put back at the very beginning on the other board was that we're going to come up with hundreds of examples. And the reason I'm saying that is because we now have learned that any time you have a function and this function is the dependent variable and this is the independent variable, we can always find out a meaning of a definite integral by multiplying the units. And I'll just give you one example. Say you had some gravel operation where the amount of unprocessed gravel arriving came in at a rate of this many tons per hour. So you had some, and it can be a really complicated function of t. It could be the sine of t times the square root of t squared plus 73. Something really complicated like that. And if this is t in hours, what's going to happen if we take the definite integral from 1 to 4? If we took the integral from 1 to 4 of u of t dt, what are you going to get? Tons per hour times hours, or Tons. It's going to be the number of tons of unprocessed gravel that arrived at the plant between time 1 and 4, which might be something that you want. So the point I'm trying to make is, anytime you have a function, there might be an application of an integral. And then again, there might not, but in many cases there will. And I think you're going to see that the real value is when a function happens to be a rate with respect to time. Because when you multiply a rate with respect to time times time, then you're accumulating whatever happens to be up here. In this case, tons. When that was velocity, you're increasing meters. So anyway, we have now finished up on integrals. We've finished up on derivatives. So the two most important things in this class we have done. So all we really have to do is look at some more functions that might be important and how to take integrals and derivatives of those. So, take care.